welcome to EC Electronics. This is a video on ISRO Technical Assistant exam preparation, and in this video we are going to see some more questions from the satellite communication subject. We were seeing the questions from the satellite communication in the previous video also. In this video we'll be seeing some more questions. Okay, and also I've been receiving a lot of requests to explain the syllabus of electronics for ISRO Technical Assistant, and also I have received requests to tell about the books that you can refer for the preparation of this technical assistant exam. So I'll be doing a separate video on the books and the materials, and in this video I have shared the electronic subject syllabus, or the subjects you need to prepare for the technical assistant exam, and I've given a description in the end of this video. Okay, so let's see what is the first question for today's class. A 20-meter antenna gives a certain uplink gain at 5 GHz. For getting the same gain at 25 GHz, the antenna size should be option A 100 meter, option B 80 meter, option C 20 meter, and option D 4 meter. Now, in this question, that is for answering this question, you should know one relationship. That is the basic relationship which actually lead to all the modulation techniques and all. That is, the frequency is inversely proportional to the antenna diameter. That is, antenna diameter is proportional to 1 by frequency. So, this is actually the key principle behind the modulation techniques. In order to reduce the antenna diameter, actually we are going to modulate a high frequency carrier wave to transmit the message signal. That is, if we are increasing the frequency, we can reduce the size of antenna, right? So, this is actually one of the key principles behind the modulation techniques, or this is actually something which led to the modulation techniques. Now, in this question, they have given that 20-meter antenna is giving a certain gain at 5 GHz. Okay, so what is the antenna size if the frequency is increased as 25 GHz and we need the same gain? That is, in order to get the same gain at 25 GHz, what should be the size of antenna? So, the simple technique to do this problem is that if you see the frequency was earlier 5 GHz and it is multiplied by 5, that is into 5 to get 25 GHz. And also we know that the relationship of antenna diameter and frequency are inverse relationship. So, if the frequency is increased by 5, then the diameter should be divided by 5. So, divide by 5 to get the antenna diameter or antenna size. So, here it will be 20 by 5, which will be 4. So, the answer for this question will be 4 meter. That is, if the frequency of your signal, or the frequency if it is increased by some factor, means the antenna size has to reduce by that factor. So, if 5 into 5 will get the frequency, that is 25 GHz, then divide your antenna size 20 by 5 and 4 will be your new antenna size. So, if frequency is increased, means antenna size has to reduce. So, that is a simple principle behind this, and the answer for this question is option D, which is 4 meter. So, for answering this question, you should know this relationship. The following is not a satellite subsystem. So, they are asking out of this which is not actually a satellite subsystem. Option A, ground station. Option B, power system. Option C, telemetric tracking system. Option D, communication system. So, out of these 4 systems, the power system is a satellite subsystem. It is used for delivering power and energy to the satellite. Then, telemetric system is required to receive telemetric signals, that is from the sensors and actuators. That is, to receive the signals from the satellite, we need a telemetric tracking system to track the various things of the satellite. Okay, so we need a telemetric tracking system. Communication system is also an important part of the satellite subsystem, and there are other subsystems like propulsion subsystem. So these all are part of the satellite subsystems. Now, what is ground station? Ground station is not actually a satellite subsystem. It consists of a transponder which is used for transmitting and receiving signals from and to the satellite, and also to communicate with the satellite. So it consists of the ground station is not a part of your satellite subsystem, but rather it consists of a transponder which is used for transmitting and receiving the signals from the satellite. So for this question, your correct answer is option A, because the ground station is not actually a part of your satellite subsystem. Okay. So the next question is, how does troposphere affect the satellite signals? So we know that there are various layers of atmosphere, troposphere, stratosphere, ionosphere, likewise. So how this troposphere is actually affecting your satellite signals? Option A, reduced velocity. Option B, reflects the signal. Option C, refracts the signal. And option D, none of this. So when the satellite signals are passing through the troposphere, what happens is that it will compress the velocity of the signal, or it compress the wavelength of your satellite signal. So it compress the wavelength of signals, which will lead to the reduction in the velocity. Whereas when the signal is passing through some other layers, the signal's velocity will get increased. But when passing through the tropospheric layer of the atmosphere, the reduction in velocity is happening. That is, the signal's velocity is actually reduced. Okay, so the correct answer is your option A, that is, velocity reduces, or reduce velocity of your signal. A transmitter outputs 8.5 watt with a 11 dB gain antenna. Cable loss is 1.2 dB and connector loss is 0.25 dB. Assume antenna directly pointed to satellite. Find the uplink EIRP. Now, we are not familiar with this EIRP till now. What is actually EIRP? EIRP is effective isotropic or isotropically radiated power. That is EIRP. Okay, so this EIRP is actually a power budget which takes the sum of all power gains and losses. That is for an uplink. So here it is asking the uplink EIRP, right? So EIRP for uplink is defined as transmitter power in dBm. This term is very important, dBm, plus antenna gain in dB minus connector loss in dB minus cable loss in dB. So this is the equation to find your EIRP. Okay, that is taking the sum of all the gains and the power and reducing or subtracting the losses, which is the cable loss and the connector loss. We know that any system is associated with some losses also. So to calculate this power budget, we need to reduce those losses. So in this question, they are asking to find the uplink EIRP. And what all things are given? The transmitted power is given, the cable loss is given, gain is given, connector loss is also given. But if you see, the power is given in watts. Okay, the power is 8.5 watt, but we need the power in dBm. Okay, so first we need to actually convert the watt power into dBm value. So for that, I'm going to write the equation to find the power in dBm. Okay. So power in dBm is defined as or is equal to 10 log 10 P out by P in where P out is your output power, P in is your input power. And for this, that is for power, for calculating the power in dBm, this P in is defined as 1 milliwatt or 1 into 10 raised to minus 3 watts. So this is your power in dBm equation. Or we can say that power in dBm is actually the power which is expressed in decibel relative to the milliwatt power, or decibel value relative to milliwatt power, because here we are assuming or setting the input power as 1 milliwatt, 1 milliwatt or 1 into 10 raised to minus 3 watts. To calculate this, that is the power in dBm value, by substituting your P out as 8.5 watt, you will get the answer is 39.29 dBm. So you have all your required values now. Your power in dB, your antenna gain in dB, cable loss and conductor loss in dB. Now to find the EIRP, what you need to do is substitute the value in the equation. That is, add the power in dB and gain in dB values and then subtract these values from that. So 39.29 dB, which is your transmitter power, plus gain, that is 11 dB, this dBm, minus the losses, that is 1.2 dB minus 0.25 dB. Okay, so if you take the sum of this, or if you calculate this, it will be 0.29, 9 plus 1 is 10, 50.29 minus 1.45 dB, right? So 50.29 minus 1.45 is 48.84 dB is your value. Okay, so the correct answer for this question is your option A, that is 48.84 dBm. This dBm value, it is the effective EIRP for your uplink, or effective isotropically or isotropic radiated power. Okay, so this is actually a power budget which takes the sum of all gains and reduces all the or subtract all the losses. So for that you have to add the transmitter power in dBm and gain, then subtract the connector and the cable loss from that. Okay, so the correct answer is option A. So these are the questions which I have included in this video. We will see with some more examples and some more questions from different subjects of electronics in the next videos, that is in the upcoming videos of technical assistant exam preparation. Okay, so if you like this video, please do give it a thumbs up and also share this video with all your friends. And if you want more videos, please do subscribe to the channel. And also I have included the electronic subject syllabus after this. So please do watch it and start your preparation for the exam as soon as possible.